How do you find the area under a function? For a linear function like this, it's pretty easy. All we need to do is find the area of a rectangle. For other linear functions, we can break the region into the areas of a rectangle and a triangle. But what happens when you're trying to find the area under a curve? Here, things get a little different. But before answering that, pause. You might be wondering, why does finding the area under a function even matter? This isn't just a random math trick, it's actually very useful. Imagine the y-axis represents your speed on a trip, measured in miles per hour, and the x-axis represents the time measured in hours. The area under the function represents the total distance traveled. For example, if A represented hour 1 and B represented hour 3, then the area under the curve between 1 and 3 is the total distance traveled between those hours. This works because multiplying a rate by a time gives a total amount. If this doesn't make sense right now, don't worry about it. We'll see it at play later in the video. Okay, so how do we find the area under a curve? We start with something we already know, the area of a rectangle. Suppose we divide the graph into 3 equal sections. For each section, we draw a rectangle whose height is given by the function value at the left end of the section. How closely do the sums of the rectangle areas resemble the actual area under the curve? Not great. So let's improve it. Instead of 3 rectangles, let's use 4. How's it now? Better. Okay, one more rectangle. Oh yeah, this looks a lot better. As you can see, as we use more rectangles with smaller widths, the rectangles fit the curve better, and the approximation improves. Now, for these rectangles, we used the left side of each section as the height of our rectangles. What would happen if we used the right side instead? Well, just like when we used the left side, at first the rectangles aren't very good approximations. But the more we use, the more accurate our approximation becomes. So it's the same idea here. The idea of using rectangles to approximate the area under a curve is called a Riemann sum. As we just saw, there's the left Riemann sum, which uses the left side of a section as the height of the rectangles, and then there's also the right Riemann sum, which uses the right side as the height. There are also a couple more Riemann sums that are very similar. There's the midpoint Riemann sum, which uses the middle as the approximation for the height, and there's also the trapezoidal Riemann sum, which finds the average height of both sides and effectively calculates the area of a trapezoid. Okay, so that's the intuition behind the Riemann sum. Let's see a real example of Riemann sums in play. Here, we have the function x squared plus 3. Let's try to find the area under the curve from x equals 0 to x equals 3 using a left Riemann sum. And for the sake of calculation, let's divide this into 3 equal subdivisions. This tells us that each subdivision will have a width of 1. Okay, so we're looking for the left Riemann sum, which means we'll be using the left side as the heights of our rectangles. This means our first rectangle will have a height of the function value at 0. That's 0 squared plus 3, which is 3. So our first rectangle has a height of 3 and a width of 1, which makes a total area of 3. Okay, now for our second rectangle, we use the function value at 1 as the height. That's 1 squared plus 3, which is 4. 4 times 1 is 4, so that's the area of the second rectangle. And our third and final rectangle will have a height of f of 2. This is 2 squared plus 3, or 7. 7 times 1 is 7, so this rectangle has an area of 7. Now our total approximation is 3 plus 4 plus 7, or 14. Now, just from looking at the graph, you can see that it's probably not a very accurate approximation, but that's the gist of how you can use a Riemann sum to calculate the area under a curve. At this point, we understand the idea. We're just adding a bunch of rectangle areas together. But as you can tell, notation-wise, this can get very tedious. So now all we need is a clean way to write the notations for a Riemann sum. To start, let's call the total number of rectangles n, and let's assume that all the rectangles have an equal width. Since each subdivision is equal, then that means each rectangle's width is the total interval divided by n. The area of each rectangle is its height times its width, and we know the width, the interval b minus a divided by n. So what is the height? Well, if we use the left Riemann sum, then it would be the left edge of each section. In a left Riemann sum, the first rectangle's height is determined by the left endpoint, which is a, or which we can call x naught. The height of the first rectangle is simply the function value at x naught, or a. Since all the rectangles have the same width, each rectangle's height is the function value of the previous section's left side plus the change in x, or the width. Thus, the height for the rectangle at any given index is the function value of x naught plus the change in x times I. So this height times the width is the area of any given rectangle. And let's also substitute in for the change in x, or the width. So this is the area right here. The Riemann sum is the sum of all of these areas. For a left Riemann sum, the summation index will start at 0, ensuring we start at the left endpoint. We then increment by 1 until we hit n minus 1. This way, all our rectangles get their height from the left. Notation for the right Riemann sum is very similar. The height of a right Riemann sum is on the right side instead of the left side. So instead of starting our index at 0, we can just make it 1. This ensures we automatically start on the right side of each rectangle, and we increment the index by 1 until we reach n. And these are the notations for the left and right Riemann sums. Hopefully this gave you some idea of how you can find the area under a curve. These two Riemann sums are just two of many ways to find the area under the curve, and they are a huge foundation of math. If you found this channel helpful, support the channel by checking out my store at dino101math.com. The link's in the description along with the limited discount, so make sure you check that out. And as always, thank you for watching, keep working hard, and keep learning, and subscribe.